Good morning, sir.
Good morning, sir. Good morning,
Good morning,
sir.
sir.
Good morning. Have you registered on ERP for this course, Analog CMOS Integrated Circuits? Because on the ERP, I had seen no student was registered for this course.
Yes, sir, we have registered.
And did
Sir,
it get
actually, the course has not been approved yet.
okay? But you all have registered for the course.
Yes,
Yes,
sir.
sir.
Yes, sir.
So this is Analog CMOS Integrated course, which I would be taking. I am Dharmen Bulchandani. Right? And this online will be till next week, I suppose. Then from 14th, you have an exam for your fifth semester.
Yes,
Yes,
sir.
sir.
Okay. And those exams will be for a week. And again, from 21st, we are going to have our offline classes.
Yes, sir.
Okay. And who is the CR of your class? Do you have a CR in the class representative, who coordinates all these activities, say arranging the class, fixing the time? Do you have a CR,
Ronak.
class representative?
Yes, sir,
Yes,
Ronak.
Ronak. Where is Ronak? Ronak, you are the CR? Then who else? Naman and Sukriti were in fourth semester. And in fifth semester, where is Ayush and Sukriti Bora? Sukriti, you are there?
Yes, sir.
You are representing the class. You still hold the responsibility of being CR.
Sir, if somebody else would take the position.
Where is Ayush? So someone has to be the CR of class. Naman, would you take the responsibility?
Sir, for this subject or for all subjects?
See, the CR will be for a whole semester. He has to take responsibility. There can't be a individual CR for a single subject. Because you should have one CR who would coordinate. Because in this COVID times, sometimes the classes are going to be online, sometimes it is going to be offline. So, Naman, do you agree to be CR for this semester?
Okay, sir.
Okay. So you just mail me your mobile number also, and anything would be there regarding the class timings and this. I'll coordinate with you.
Okay, sir.
You have my email ID, na?
Yes, sir.
Okay. So today I'll have an introductory class with you. I'll tell you about the books, test book that we are going to follow and the reference book, right? And why we need to study the analog CMOS circuits, right? Is the slide visible to everyone?
Yes, sir.
So Analog CMOS integrated circuit. This is a 3 credit course. Normally we have 3 lectures per week, but during this online we'll be having 4 lectures per week. And once it comes to offline, you will be having a lab classes also. I hope this would get again. We would be having 3 lectures per week, right? And the test book that we would be following for this is Fundamental of Microelectronics by Behzad Razavi. And this is a Wiley India publication, right? It is edition is 2012, and it is a cheap book. That is, the cost is cheap. That is, you can get this book in say 250 to 300 rupees, in range of 250 to 300 rupees. And then we have a reference book, Analog Integrated Circuit Design by John Martin. It is John Wiley, 2nd edition, and 3rd edition has also come up, right? So this would be the reference book. So our first class is Introduction to Analog Design, right? So why you require to study analog design when lot of things are possible in digital circuit design? We'll see that many things we are able to do in the digital domain, that is filtering, transmission, modulation, demodulation, we are able to do in a digital domain, but there are certain fundamental things which you can't avoid being processing in an analog domain, right? You, even if I speak, how the sound is getting transmitted, it is being picked up by microphone, right? And depending upon the loudness of the voice, it is going to, the microphone is going to produce a electrical signal ranging from few microvolts to few hundred millivolts, right? And that electrical signal output of the microphone has to be again further amplified. It has to be filtered, and then it has to go to the ADC, which will convert into a digital signal, and then you do the processing in the digital domain, right? You can compress your this signal, particularly if you are transmitting a video signal. Then what you will have to do, you will have to compress this signal and then modulate it and then transmit it, right? And similarly, not only this voice, even any camera you take, depending upon the intensity of the light, your cells, that is the photo cells, are going to produce an output which will be, say, few electrons per second. The intensity of the current is going to be that low. So again, it has to get amplified, filtered, and converted into digital signal for further processing. There are many sensors. If you could talk about, say, if you want to measure an earthquake, right? If you want to measure an earthquake, you employ a seismograph. And this seismograph, depending upon the vibrations of Earth, produces a signal, again varying from few microvolts to few hundred millivolts. And then these signals have to be amplified, filtered from the noise, and converted into the digital signals, right? And though the design looks simpler, that there is nothing a big deal in designing an amplifier, in designing a filter, but when you do it at a very high frequency, then it is not a trivial job, because many parasitics come into picture at a very high frequencies. Parasitics are those components, say parasitic capacitance, parasitic resistance, parasitic inductance, which were not intended to be there, but because of the inherent nature, they come into picture and they try to distort the signal. Even in digital communication system, suppose you are in a building, there are many computers and they are connected through a computer network. And if you're transmitting a digital signal through this computer network, you'll see that at the transmissions, that is at the other end of the transmission, your binary signals also get distorted. It not only get distorted, also attenuated, right? So the input to this cable was a binary signal, but the output, you will see that if it is at a very high speed, then it is not only attenuated but also distorted. So again, you will have to restore the signal back to the binary form. So again, you have to have an ADC which will sense the signal and convert it into original binary signal. And sometimes we see that you have a signal that has to be transmitted and bandwidth is limited. You want to transmit your signal at a very high speed, but your bandwidth is limited bandwidth you have available. Then what we do, we employ a certain techniques where we convert binary data into a multi-level signal, right? And if you convert into a multi-level signal, we'll see that it saves the bandwidth. This is one common technique in the communication. So what you're seeing here is a binary signal which has been converted into 4-level data. So what is being done here is, this is 1, 0, it is at certain level. Then you'll see 1, 1 is at a certain level. Then 0, 1 is at a certain level. And then 0, 0 is at a certain level. So you require, say, digital to analog converter, which will generate from your binary data to this multi-level signal. Similarly, at the receiver end, you want to convert it back to the binary data. So you will require analog to digital converters. So these analog to digital converter, digital to analog converters, they are all require the knowledge of how to design an analog circuits. So then comes the disk drive electronics, that is the data stored in your hard disk of, say, your laptop, computer. And then when we want to read that data through a certain magnetic head, the output we'll see is again not a plain binary data. We see that this is associated with the noise. And when you are reading the data at very high speeds, nowadays you do have a hard disk available which work at the gigahertz. So if you try to read the data at that high speed, the output is going to get distorted. So again, it has to be restored back to the original digital signal. And again, as you all use your mobile phones, right? The receiver that you receiver has to sense, that is your receiver is going to have an antenna, and that antenna has to sense a signal at a very high frequency, right? It would be in gigahertz, right? And the amplitude of the signal is going to be again in, say, few millivolts only, right? And there are going to be unwanted interfering signals, larger in amplitude, right? So your receiver has to sense the desired signal. At the same time, it has to reject the high amplitude interferers. So you should be able to design your receiver circuit, which selects the desired signal, amplifies it, and removes the noise associated with it, which is not desirable. And this all you do it at a very high frequency. And when you do it at a very high frequency, as I had told you, there are going to be certain parasitic elements that come into picture and they may distort your signal. So you have to be very careful in designing so that there is a minimal effect of those parasitic components on your circuit. And nowadays, as we have seen that if you want to have a high-speed communication, you do it through an optical fiber. Optical fiber has its own advantage. It has a very large bandwidth, very less amount of attenuation, right? So we do transmit our signals through an optical fiber. And if you want to use an optical fiber as a medium for a communication, what you will have to do, you will have to convert your signals to the optical signals. So you need to have a transmitter circuitry involving laser diodes that converts your electrical signal to the light signals. And then you are able to transmit it through an optical fiber. And at the receiver end, you would require a receiver circuits involving photodiodes, which would convert again those signals back to the electrical signals, right? Which can be further processed at the receiver end. So all converting circuits from the electrical to optical signal are analog in nature. Similarly, from optical signal again back to electrical signal, you require circuits which are analog in nature. And you will see that there are nowadays many, we have seen that in our daily life, many sensors are there, which has automated many things. Even the vehicle which you drive, right? You have suppose you are driving a four-wheeler, you'll see in your car there are many automotive things. A lot of electronic is getting involved into. Previously, it used to be a purely mechanical. Nowadays, even your engine is electronically controlled. You have a microcontrol which adjusts the right amount of fuel air mixture so that optimum torque is obtained. You have an electronic brake system. And then there are certain safety measurement devices which are electronic. So all of you have heard of airbag? What is airbags in four-wheelers? You must
So
have
in
seen that.
case of accident, to save the driver and
What happens?
what is
How
the
it
reason?
saves the driver?
When there is a sudden shock, the airbag gets filled up and it saves the driver.
What happens when there is a certain shock?
It gets filled up with air.
Okay. So airbag systems are that you have in a bags which get inflated, right? Whenever a collision is going to take place, see, whenever an accident take place, there is a collision with a certain things, and as a collision take place, right? Uh, your airbags in the vehicle should get inflated so that before all those who are sitting in the vehicle, before they collide in front, suppose if a driver is there, what is going to happen? If the airbag gets inflated, he is not going to get collided with the steering or the another person who is sitting with him to the dashboard. So air cushion would come in between the dashboard and the passenger, between a steering wheel and a driver, right? And this should happen in, say, few seconds itself, right? Otherwise, there would be a very fatal injury. So what it has to do is, your electronics has to sense the deceleration, right? Because what is happening, your vehicle is moving at a very high speed and it collides. When it collides with anything, naturally the speed has to come down. So if the speed is coming down, there is going to be deceleration, and that deceleration has to be sensed, and the airbags have to get activated, right? They have to get inflated so that the driver doesn't have a severe collision with the steering wheel and the impact is minimized, right? So there are different ways how to detect this acceleration. Some are this sensors are capacitive in nature. What they'll, depending upon the deceleration, what is going to happen? The capacitance of the circuit is going to change, right? And the change in the capacitance is going to be measured, and it should be such that if the capacitance changes by a certain amount, your airbags has to get inflated or it has to get activated. Now, depending upon the deceleration, this plate is going to move, right? And as this plate moves, there is going to be change in the capacitance. So this change in the capacitance has to be measured, right? And it has to activate your airbags. And you'll see that this change in the capacitance is going to be less than 1%. So the small amount of change in the capacitance has to be sensed. So this sensing system has to have a high sensitivity. Sometimes it is difficult to measure the absolute change in the capacitance. So what you see in the figure B, you have a plate moving, and this movement of the plate is going to change both the capacitance. It is going to change the capacitance C1 and it is going to change the capacitance C2 because the distance between the plate has changed. And because of change in the distance, your C1 has, one of the capacitance has increased, or other capacitance has decreased. So now it is easy to measure the relative change in the capacitances. So these are the techniques which are employed in analog circuits to sense. You should have sensors which have a high sensitivity, and to increase their sensitivity, you employ such techniques, right? Because what we saw in the figure A, there is an absolute change in the capacitance, and absolute change in the capacitance is very, very small and it is difficult to measure. However, whereas the change in the capacitance of C1 and C2, that is easy to measure. And we see that there are many circuits in our daily life, many sensors in our daily life, which are being used. And associated with these sensors, you have an analog circuitry, right? Because the output of the sensor is going to be very small, and whatever is the output, that has to be converted into electrical signal. It has to get amplified. It has to get filtered from the associated noise, and a corresponding action has to be taken accordingly. Why the analog design is challenging? It is very easy to design digital circuits, right? Because digital circuit deal primarily with the speed and power trade-off, right? You have a trade-off between the speed and power. That is, if you want to increase the speed, you'll have to increase the voltage. You will have to give more current so that if this current is more, it is able to easily charge and discharge. In digital circuits, your binary signal, you have a binary signals 1 and 0. And binary 1 is when the output voltage is 1, and 0 is when the output voltage is say a very low value. So basically it is how fast you are able to change the switch from one level to another level. And if you want a higher speed, what you'll do, you'll increase the voltage so that the current increases. If the current increases, it is able to charge the output to very quickly. And similarly, it should be able to discharge the output if you want the change the signal from high value to low value. Whereas the analog circuit deals with the multi-dimensional, right? There are multi-dimensional specification. You have to have a trade-off between speed, power gain, precision, supply, linearity. There are many things which are taken into account when you design an analog circuits, right? And due to speed and precision requirement, analog circuits are much more sensitive to noise, crosstalk, and other interference. You'll see that the analog circuits, they are sensitive to noise, they are sensitive to the crosstalk, right? And interference. Whereas the digital circuits, you don't have such a major challenge. Can anyone of you tell me why? Why analog circuits are more sensitive to noise, crosstalk, interference, whereas digital circuits are not? You have read digital circuits in your 5th semester, no? Why digital circuits are immune to noise, crosstalk, and other interference, whereas analog circuits are not? Yes, anyone in the class? Yes, anyone can tell me. Why digital circuits are immune to noise? पढ़ा है कि नहीं पढ़ा है डिजिटल इंडिकेटेड सर्किट्स था कोर्स Yes, Sukriti, are you there?
Yes, sir.
You tell me.
Sir,
What?
one reason is that the normal signals which we have in nature are analog in nature,
Yeah,
so it will affect the analog signals. And for detecting analog signals, we need to determine the voltage level. And for digital signals, we just need to determine one or zero. So I think that is the reason.
yeah, you are right, very much right. But can you elaborate it further? Why digital circuits are immune to noise? They will be not perfectly immune, but they can sustain the noise. What is in digital circuits that they are able to sustain that noise?
Filter, sir.
No, filters are not, you don't employ filters in, say, digital circuits. They would be employed later on. But there is something inherent in the digital circuits. You all have studied, I'm sure, in your 5th semester. Have you
Digital
read the,
signals,
yes?
digital signals do not have the effect of phase shift, whereas analog signals have.
That is, you have read this noise margin, concept of noise margin? Yes or no? Have you read this noise margin concept in digital circuits or not? What is noise margin? Huh?
No, sir.
Noise margin was not taught to you?
Sir, is line coding the reason?
No, not line code. You tell me you have read this digital inverter circuits you have read in digital CMOS circuits, ना? पढ़ा कि नहीं पढ़ा है? इन्वर्टर सर्किट तो पढ़ा है? इन्वर्टर्स पढ़े होंगे तुमने, CMOS इन्वर्टर.
Yes.
हाँ, CMOS इन्वर्टर में तुमने नॉइस मार्जिन नहीं पढ़ा क्या? बताओ. अच्छा, ये बताओ नॉइस मार्जिन. हैव यू हर्ड दिस टर्म नॉइस मार्जिन और नॉट?
Yes, sir.
You have heard. What is this noise margin? You tell me. See, in digital circuits, what are this 1 and 0? 1 is a certain high voltage. If it is in a positive logic, 1 means, let us take it as a 0 and 5 volts, right? 1 means it is 5 volts and 0 means it is 0 volt. Isn't it?
Yes,
Yes
sir.
or no? Right? Now, your digital circuit, there is your input signal. If it is 1, that means it should be 5 volt. Now your digital circuit will, how long will it take that this is 1, even if your voltage goes down? Suppose now from 5 it becomes 4. Will it take it as 1 or not?
It will take it as 1.
Okay. If it goes to 3.5 volts,
Still 1.
it will be 1. And then again, if it goes to 3 volts,
1.
okay, 2.5 volts,
So at this point, it will get confused. 0 or 1.
okay. So your idle inverter, say idle digital inverter, should have a noise margin from 5 volts to say 2.5 volts. If it is signal is more than 2.5 volts, it should take it as 1. If the signal is less than 2.5 volts to 0, it should take it as 0. So the idle inverter should have a noise margin of say 2.5 volts. But practically the circuits don't have that amount. They would have all the signals lying between 5 and 3, depending upon the design of inverters. If it is between 5 and 3, it will take it as 1. If it is between 2 and 0, it will take it as 0. Now, if this circuit read your signal as 1 for a voltage which is 3 volts, then we say that it has a noise margin of 2 volts. So even if a noise comes and deteriorates your input from 1, say 5 volts to 3 volts, it is still able to read it as 1. Similarly, if there was a 0, if noise comes and takes your 0 level to say 2 volts, and if your inverter reads it as a 0, we say that a lower noise margin is 2 volt, higher noise margin is again 2 volts. And this may vary. You may have a higher noise margin for a upper bit level and lower for a lower bit level. So depending upon the design of circuit, your noise margin could vary. So best design is the one which has a maximum noise margin. That is how you design an inverters. So one of the criteria is you should have a large noise margin. Its speed should be different criteria. Speed should be high. The power consumption should be low. Right? So you have a concept of noise margin in case of digital circuit. Whereas in analog circuit, it is nothing like that. You have an exact linear relationship between the input and output. Any noise comes, if it is not suppressed, it is going to get reflected. So our analog circuits are sensitive to noise. Again, the crosstalk is that any one intended signal which was running on a certain line, if it gets coupled to the other line, you say in a crosstalk. See, there are two signal lines going on, and one line is carrying the signal, another is carrying a clock. If you have a parasitic capacitance means that the capacitance was not intended to be there, but because these two lines are conducting and you have an insulating region in between, what happens? Clock runs at a very high speed. This clock signal would get communicated to the signal line, and it is going to generate a noise there. So you will say that your clock line is cross-talking with the signal line. And if the signal line is analog in nature, it is very sensitive to such crosstalks because you don't have a concept of noise margin. Whereas in digital circuit, you have a noise margin. So designing of analog circuits, which not only have to have a high speed, precision, these are much more sensitive to noise, crosstalk, and other interferers. You have to design your circuit so that these are immune to such noise, right? Special care has to be taken when you do a layout of these analog circuits. Is that clear?
Yes, sir.
Analog circuits are much more sensitive to second order device effect. All of you must be familiar with MOSFETs, metal oxide semiconductor field effect transistor. You must have read MOSFETs, right?
Yes, sir.
No. Now this MOSFET have a second order device effect, which is one is known as the channel length modulation effect, another is the body effect. Are you familiar with this? What the channel length modulation effect is and what is the body effect? Are you familiar?
Yes, sir.
Okay. You must have seen in the digital circuit, these factor doesn't affect the performance. The channel length modulation effect as well as the body effect. Whereas we'll see in the analog circuits, these are going to affect our performance. So we have to be very careful because of this second order device effect. We say that when the device is ideal, MOSFET behaves ideal, you don't have this channel length modulation effect, you don't have body effect. But practically, when the device is there and these effects do come into picture and they affect the performance of analog circuit. Another why this is challenging is that high performance analog circuit can really be can rarely be automated, whereas digital circuits can be easily automated. Depending upon the specification, you write a specification, you specify the specification, write your whatever the design specification and say your any HDL language, whether it is VHDL or Verilog, when you have correctly written your specifications in Verilog VHDL, it automatically gets transferred into RTL level, from RTL level to transistor level, and from transistor to the layout level. So given a specifications, there are tools available which is going to convert your specification into the exact layout of the circuit. Whereas in analog circuit, this is not possible. Because there are many trade-offs involved and it requires the experience. That is how you have to design the circuit, how you have to lay out the circuit, because there are many parameters which has to be optimized. And with the experience only, we will come to know that if you are doing a layout in such a way, you are able to avoid the parasitic effect, you are able to avoid the variabilities, because analog circuits are very sensitive to this. Say your parasitic elements and variability. What is this variability? Variability is that whenever you design a circuit, say that you are designing a transistor. So the size of the transistor depends upon what is the width of the channel, what is the length of the channel. The performance, we'll see that of a transistor would depend upon what is the width and what is the length, what is the threshold voltage of the device. That you are familiar with. MOSFET की जो current है, current depends upon the width of the channel, length of the channel, threshold voltage of the channel. Isn't it?
Yes, sir.
Now what happens when your size is getting reduced? That is, you have a transistor now available, commercial available transistor, which have a channel length of say 7 nanometer. When your channel length is 7 nanometers, say width will be 3 times more or 5 times more than that. Now, when you are working at such a low technology, that is lower dimension, when you are fabricating a transistor of 7 nanometer, is it going to be exactly 7 nanometer? No. Because your manufacturing device also has a limitations. It can easily be 7.1, it can be easily be 6.9, because your feature size has gone down. Similarly, if you have, when you are fabricating a transistor, you want to adjust the threshold voltage of the transistor. That is known as a step, which is threshold voltage implant. You dope the impurity atoms in the channel region to adjust the channel. Now, it may happen that there may be a variation. Your one transistor may have a few atoms more of impurity, so its threshold voltage is going to be less, right? So again, the threshold voltage is not going to be constant. It is going to change. You have the same set of manufacturing device, but you may have a different width, different length, different threshold voltage, because of the limitation in the manufacturing process. And as the technology has gone down, this variability has increased, right? And one typical example all of you are familiar with, you have seen the resistances. Resistances यूज किए हैं कभी लैब में?
Yes, sir.
उसमें 4 color rings होती हैं, right?
Yes.
The 4th color ring is for,
Tolerance.
yeah, the tolerance is the 4th color ring, right? So if it is in a silver color, what is going to be the tolerance?
10%.
So 10%. So if you have say 100 ohm resistance, the resistance may vary from 90 ohms to 110 ohms. If you have the golden ring as a fourth ring, the tolerance is 5%. That means your resistance is going to vary from 95 to 105, isn't it? So it is
Yes.
not going to be exactly 100 ohms. So there is a variability in the value of the resistance itself, right? But still your circuit should, seeing that it should work perfectly with the 95 ohm resistance also, it should perfectly work with the 105 ohm resistance also. It should be able to tolerate this variability of resistances. Similarly, in analog circuits, you may have a MOS transistor which have dimensions where that W may change, L may change, threshold voltage may change, right? And this variability becomes more pronounced as your feature size goes down. So you should be able to design your circuits. You have to, in fact, handcraft those. You have to select those WL, and then you also have to do the layout, which you have learned through over the years of experience. So automation of analog circuit design is difficult, though we are able to do it at a certain levels, but not 100%. Automation is there. So 100% automation is not there. Whereas in digital circuits, the 100% automation is there. The other problem is that the modeling and simulation of analog circuit is still problematic, requiring experience and intuition. You'll see that before, when you're thinking of say a certain product, you do a system level design. When you're doing a system level design, you will first see that whether it is going to work or not. So you have to model your circuit. Now, modeling of analog circuit is quite difficult, right? And we'll see that when you're simulating analog circuits, you must have done the simulation of digital circuits. When you are simulating analog circuits, and if your circuit is quite big enough, it takes months to simulate and give you the results, right? And then you also have to consider those model levels which consider all the effects. So you must have used the models for the transistor in your digital circuits. Similarly, when you use a models for analog circuits, the MOSFET models have to consider all the effects, all the secondary effects, and many other effects into so that it gives you the correct results. So it is not a trivial job designing of analog circuits. You have to learn, and experience makes you a master. How many of you know the game of chess? You have heard about chess, no?
Yes, sir.
You know, how many of you play chess? Okay, quite number of you. So when you know that how your that is how the movements are done in the chess, it is does not make you a master of chess player. You should learn the art of playing a chess, right? Then only you are able to win the game, isn't it? So similarly, analog circuit is like that. It is like a chess. Just because you know how the pieces move doesn't mean you know how to play the game. So if you know that how the MOS transistor is going to work, you are not going to be the master in designing analog circuits. There are many things which will make the analog circuit to work properly, right? It has not to be only properly sized transistor. There are certain bias which comes into, you have to properly bias the circuit, right? You have to properly lay out the circuit. Then only the analog circuit works perfectly well. So it is not very difficult also. So in this course, we'll be touching upon the basic analog circuits. Only the thing is that you have to be regular in your lectures. And when you go back, if you're regular in the lectures, you are attentive. When you go back and see the book or read the material, it will be easier for you to understand. So that is what I would expect you all to be the regular in class. See, you all are going to pass out with a degree of BTech in electronics and communication engineering, right? So when you pass out with a degree of BTech in electronics and communication engineering, you should feel confident that you are able to design one amplifier, at least one amplifier circuits, right? भले वो जिंदगी में तुम्हारे जॉब में काम आए ना आए, but inner satisfaction is going to you that yes, I am being an electronic engineer. I know how to design one circuit, which one amplifier circuit itself, at how it works. Do you agree with me or not?
Yes, sir.
Yes,
Right? And I would say that this subject is not at all tough, though it may be not, say, very easy to follow. But if you are attentive in the class, I'll say that it is much easier than the physics that you have studied in your class 12th. Right? Class 12th की सबने physics master की है, तभी तो यहाँ पे हैं. Isn't it? You all are in MIT Jaipur because you have done well in your at least physics course, right? Do you agree with me or not?
Yes, sir.
And all of you are above average. That is why you are here in NIT, right? So have confidence in yourself and just be regular in the class. ये मत सोचना कि ये electronics है, जॉब में काम आएगा कि नहीं आएगा. But I tell you, if you develop a habit of, say, given any task to you, if you develop habit to work hard and concentrate and complete that task, that habit is going to remain lifelong with you. जॉब में भी कोई जाओगे, कोई भी प्रोजेक्ट भी मिला तुम्हें, सॉफ्टवेयर प्रोजेक्ट भी मिला, वहां भी रिक्वायरमेंट यही होगी कि हार्ड वर्क करना है, कॉन्सेंट्रेट करना है, फोकस होके रिजल्ट्स लाने हैं. एंड द थिंग्स आर गोइंग टू चेंज. तुमने कभी C++ चलता था, फिर जावा चलता है, आजकल पाइथन चलता है. There is going to be the change itself. But if you develop a habit of doing hard work, remaining focused, then that habit is going to be with you throughout your life. And it is going to be helpful to any field where you go. So the task that you have got, that you are in 6th semester, and this is one of the courses that you have to study. So come to the class regularly. If you have any doubts, you can always ask me. And it is not really tough. Only you have to be attentive. You have to be concentrated in the class when it is being taught. Right? If there are any questions or anything that you want to ask me, you can ask. Right? So if there are, I'll end my class here, lecture here itself. Right? And the next class we have on Friday. So I'll end the class here. Friday we have a class from, say, it's 12 to 1 or 11 to 12.
12 to 1.
So we'll meet on Friday, 12 to 1, right?
Thank you, sir.
Okay.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.